To start session one, we're going to have a talk being given by Minhaj Almam. So, Minhaj is an assistant professor at UNC Charlotte. He also has an affiliation with Stanford, and he's going to be telling us about a piece of work he did in collaboration with a number of institutions that relates to how you can examine the construction, the training of models that examine different types of eye conditions, but he took the path of training this in a federated manner. And so with that, I'm happy to hand over to him if he's online. Great, he is. Thank you, Minhaj, for joining us today. I apologize that we don't have a camera for you to see everyone here, but it's basically a room with a number of people who are just super excited to hear from you. I'll hand over to you now.
That's great. Thank you for the intro. Great to be here. I wish I was there in person, but Zoom it is. My name is Minhaj. I'm currently the director of the Quantitative Imaging and AI Lab at UNC Charlotte. I do have some collaboration and affiliation with multiple institutes here, Stanford and Illinois more specifically. So today I'm going to talk a little bit about federated learning and its use of diagnosis in macular degeneration or overall in retinal diseases. So most of the retinopathies are ocular manifestation of systematic diseases. For example, diabetic retinopathy is ocular manifestation of diabetes, and nearly 40 to 45% patients with diabetes are prone to vision impairment from DR. And it's projected by WHO that by the year 2040, it's going to be more than 200 million people who will be somewhat affected by this kind of vision impairments. In this kind of retinal diseases, what happens is that there's retinal pathologies like aneurysm, exudates, and hemorrhages that affects your retinal tissues, and there's a reduction of oxygen. Because of that reduction, there's a protein called VEGF, or vascular endothelial growth factor, that signals our brain that we need more oxygen. And the only way the brain can react to that is create more blood vessels, so that blood vessels can take oxygen to those retinal tissues. However, because this growth of these abnormal blood vessels are abnormal, they leak, and there's hemorrhages, and that can lead to vision impairments. So that's one of the main ways of getting affected by systematic diseases. AMD, the disease that I'm gonna be mostly talking about, is also a retinal disease, mostly affect the macula, which is, I don't know if you can see my mouse is around here. We're looking at the retina here, and it has become a global pandemic. The rise of AMD disease in population correlates with the increase of mean age of human, because there is a much more older population globally because of the mean age has increased. And that's why AMD is prevalent in American and European countries, and nowadays it's showing its prevalence in Asian countries as well. AMD causes manifestation of this kind of pathologies like drusen and liquid formation, and that affects the macula, which is the center of our eye. And this is what a person with impairment with AMD, their vision looks like. So we can see that there is a prevalence of retinal disorders, and millions of people have already been affected by, is being affected by these retinal diseases. And this includes adults and children. So there's a need for automated diagnosis and assistive technology for managing these diseases. Imaging actually plays an integral part in diagnosing these retinal diseases. A sample here, this is called optical coherence tomography, OCT, and optical coherence tomography angiography, which shows structural and vascular information and flow information in the retina. So So this is captured in devices in our lab where we can see the vasculature and retinal structures in the cross section, and also a 2D projection. So overall, these OCT modalities provide structural, functional, cross-sectional information on retina. Um, and we can see here like high resolution vasculature. If there's a vessel dropout, then we can see the onset of the diseases in these imaging modalities. So, and also there has been quantitative features, imaging biomarkers that have been developed, especially by our lab, which can correlate to microvasculature and foveal changes in the retina. And these features give a measure of geometric and textural complexity, and are very good in identifying different stages of the disease. However, uh, although these features are really, really useful in identifying stages and pathologies, there's a need for artificial intelligence backed models that can do some work for us. So, in the field of ophthalmology, AI has seen huge success, especially in triage. So the idea is we use AI to triage people. For example, if you go to a point of care doctor, your retinal image is taken, and then it's companies like Digital Diagnostics, INUC, Retina AI, which have been FDA approved. They mostly work on triaging. So it will flag you that you should go see an ophthalmologist or not. And then the idea is that you use those features and like other advanced imaging techniques to actually diagnose, manage your treatment. So AI is more mass scale. So that's where this methodologies come in. So importance of AI in ophthalmology is that it enhances the diagnostic accuracy. It's much more scalable. It helps monitoring disease progression. Like it's very good at time series data, like progression, prediction of onset, etc. And it's cost effective because for triaging, you don't need a doctor there, right? You just can take a patient's image and then we can find out referable versus non-referable people. So now, what is the need for federated learning in ophthalmic diagnostics? A major limitation for actually the clinical deployment of these AI algorithms is the need for large amount of well-curated data sets and well-curated and labeled data sets. And there are numerous barriers to building and hosting these large central repositories and multi-institutional data sets because there's concerns about data sharing, compliance, regulatory issues, and hospitals are generally very strict about sharing their data. So there's a clear clinical need for a robust AI model training framework that can leverage this multi-institutional data without compromising these data sharing concerns. And that's where our lab thought about using federated learning or distributed approaches to see if we can really use federated learning for ophthalmic diagnostics. It can provide data privacy and security, access to diverse data sets from subpopulation spectrums. It can allow collaboration without really sharing the data, optimize some of the resources, real world application scalability, because now you have a robust model that can be tested in different settings. So that brings into the first project that I'm going to talk about is the real goal was basically to see if federated learning models, how they compare against local and central models. So objective was basically identifying AMD versus non-AMD patients using bunch of public and private data sets. Fortunately, there are a couple of open source data sets in OCT shared by researchers. And then we have collaboration at North Carolina with Wake Forest, and then Illinois and Stanford, where we got a bunch of OCT images with a wide spectrum of AMD uh, labels. So some example of AMD patients we can see here, pathologies like this is advanced dry AMD, which is GA. You can see a tumor-like thing here. And there's also wet AMD where there's like a fluid accumulation in the patient's eye. So so the general framework, so we did use Flower as our framework, and then the general framework is probably known to most of you. Is basically we treated each of the data sets as a separate node, and then there was local model that was trained on the local data set, and then the parameters were updated and aggregated globally, and that parameters were shared to local data sets. And we found out that, and we also tried different aggregating methods, like not only just averaging, tried FedProx, SR, MRI, APFL, etc. And we tried different models to compare the likes of like ResNet, GoogleNet, and more larger network like vision transformers. And this is published in this paper, so if you're interested in reading more, feel free to take a look. The summary is basically we saw that the federated learning models outperformed each local model, and even were comparable to a central model, where a central model had access to all the data sets. A federated learning model did not have access to all the data sets, but it has access to the parameters. And aggregating methods do affect the performance, because we found out that some methods worked better than the others. And we also found out there's a need for domain adaptation, which is a really important factor in using federated learning for medical applications. We saw that because each institutions, for example, Chicago has more African American population, Wake Forest has more white population, Stanford has more Hispanic population. So we saw that because the data set is coming from different subpopulation spectrum, there are some issues with the federated model converging. So I think in our future work, we're planning to work on some domain adaptation methods where all the domain can be converged into a singular domain. The next project was basically using the same methodology for multi-class. Here, the challenge was to because we didn't have overlapping labels in each institutions. For example, I am doing a 5-class classification for 5 diseases or 5 stages of AMD. Not necessarily all the institutions have the same labels, and we didn't want to have that because that's the real life clinical scenario. So what we did is we use a self-supervised method called mask image modeling, where we pre-trained all of our data sets in a federated learning manner. And we pre-trained to mask part of the images and then train a model to reconstruct that. Our hope was that would give us a nuance learning of the model of those images coming from different labels. And then we use that final, the weights and fine-tune that on for different particular tasks. And this was the framework. Basically, all the institutions contributed to MIM training, and then final FL aggregated model was used for fine-tuning. And the result summary was, we're still kind of this ongoing work, is that we also saw that the federated learning models outperformed each local model for multi-class classification, even if when each local institutions don't have all of the labels. And the MIM weights really improve the performance compared to generic weights. There's also need for domain adaptation there. And in our future work, our question was, can we replace this kind of self-supervised methods and use just federated learning for multitask learning? I think Virginia was talking about multitask learning. Some of her work has explored this. And this is something we're planning to do, for example, using data maps or task tagging to see if we can just use federated learning domain for multitask learning. Some of the challenges that we have faced in applying federated learning, especially in retinal images, is that the device oftentimes is not device agnostic. Like device and acquisition protocols in retinal images actually affect the performance, patient demographics, and sometimes there's an issue with privacy versus accuracy, and all those. So these are probably the research directions that we're gonna follow in the future. And that's all I had. Thanks so much for having me here, and I'll answer any questions. And thanks to our collaborators, and we have been recently funded by the NIH, so I'm really grateful for that support. Thank you.
Thank you so much. So we have time for a couple of questions, if they're in the room or online. We've got one question here immediately.
Hi, thank you very much for your presentation. From the patient's perspective, what's the benefit of using these kinds of AI detection for AMD? Once, as far as I know, it's not really curable. And would it be interesting to explore in the future how well AI federated learning can predict the evolution of these patients? Thank you.
Great question. So AMD is technically, there is some interventions there. For example, you can provide anti-VEGF injections, which is basically actually a huge area of research to predict how many anti-VEGF injections you need to provide for a patient to get better. For example, if you can see some of the images of AMD, like this one, there's fluid accumulation there. So if you provide this injection, this goes down, becomes like normal. So AI can predict, for example, from baseline, how many, and it's almost like chemotherapy. Like some patient really responds really well and they get better, and some patients don't. So it's very important to have diagnosis, early onset predictions, and also prediction on like how many anti-VEGF treatment a patient might get. I would say, so AI modeling is important. And for federated learning, I feel like it's very important because federated learning is democratizing these models. For example, if you're at Stanford, then you have millions of images anyway, so you don't really don't need federated learning. But say if you are in a smaller institute which doesn't have enough data by itself for training a model, then if you are part of that consortium, right, federated consortium, then by just being part of that, you have access to a more robust generalizable model. So that's how these institutions and then the patients are being helped using these models. And then, so the second question, you mean evolution is basically, I think you're in the realm of personalized medicine where you're tracking a person by themselves. So basically the first step would be to triage and identifying the person's stage. And then you go from, for example, you would see all of their prior visits and try to predict different things. For example, for this patient, you might be able to use AI model or federated AI model to predict the response of that person to this kind of intervention. So then you are in the realm of treatment management and personalized or precision medicine, basically, which are all very interesting fields of work, and people are pursuing them as well.
Great. Thanks so much. I think we might have run out a little bit of time to carry on for the next question. But thank you so much for the talk. It's a wonderful talk, wonderful bit of Q&A just then too. So thank you very much.
Thanks, everyone.